So welcome back. I hope that you enjoyed a sandwich and maybe got a bit of fresh air, or at least a chance for your brain to take a little breather after our terminology-loaded morning. Any announcements?
We did have one question that came in that I think we might, from the webinar, that we might want to address now.
Yes,
sure.
and
I'm happy
to
pose the question to Reinhard. Reinhard, the question is this. The UARL, the unavoidable annual real losses that forms the technical minimum for the infrastructure leakage index calculation. Where did that come from, and where can I go to find more information?
So that came from an International Water Association study where they looked at numerous discrete zones, so subsections of a network where the network conditions were actually favorable in terms of relatively new networks and pipe material, well-managed pressure. And those zones were permanently monitored by having a master meter looking what's supplied into the zone and knowing also all the consumption, so very detailed monitoring of what's going in and what's the consumption. And since the zones are also relatively small in scale, you're able then to pick up any new leak that comes on, right? Because in the middle of the night, so we have a baseline. Once you removed all the leaks, a baseline. Every time there's a new leak coming on, you see an increase in flow in the middle of the night. So they monitor that over several years to see how many of those leaks that are newly developed, how long does it take for them to come to the surface, how many of those don't come to the surface, and then they got some allowances for these events, and also what is the technical minimum for background leakage. So that built the basis for coming up with those allowances for sort of an optimized system, the ideal situation. I've been using this infrastructure leakage index and unavoidable annual real losses approach for the last 15 years, and had several occasions where we worked with utilities and did some field testing where we actually came very close to those allowances, so that they hold up fairly well. I would never say it's 100% accurate, right, because every system is different, but it gives you a really good baseline of this, in theory, would be the technical minimum. And that's how it should be taken. It's not something to pin all your money on that. That's exactly the number for my system, but it's a really good range for your system to appreciate how far it could go down.
And if you're curious more about the detail of things like minimum night flow analysis or the UARL, M36, that AWWA publication on water audits and loss control, is your go-to. It's in there, it's dense, and again, we're also happy to entertain any questions either after this or via email or phone. Don't hesitate to reach out.
It's also better than Ambien if you're trying to get to sleep.
That's true, but it's not a comfortable pillow, I will say that.
I have to take that personally because I wrote. Let's talk about that later. Right? I wouldn't disagree now.
Now it's our turn to talk about intervention against real losses. We've spent some time taking a look through the water audit at the total volume of real loss and arriving at an estimate for the volume of leakage that the system has incurred. Then, by performing a component analysis, we took that total volume of leakage and broke it up into distinct types of leakage based on how you would find that leakage, whether you've already dealt with it as a form of reported leakage, whether it's insidious and ongoing, like background leakage and at such a low flow rate that you can't acoustically detect it, or whether it's an unreported leakage volume that is acoustically detectable and susceptible to being discovered through proactive leak detection. Since we now have an appreciation for the types of leakage in your system and the balance of those volumes, we can now start to think about going after those volumes of leakage to the extent cost effective. And so we have the opportunity to match an intervention tool to the type of leakage that you're incurring. When we think about unreported leakage that is ongoing in the system at a flow rate that can be acoustically or sonically detected, the tool we would therefore use to uncover that volume is proactive leak detection. And proactive leak detection aims to do a couple of things. First, in the first year of a proactive leak detection effort, you'll recover the backlog of hidden unreported leakage, stuff that's accumulated since the last time you took a look at the system. Once you've cleared the system of that unreported leakage volume, initially, your goal will then to become to combat the occurrence of new leakage in the system. So you're fighting what's known as the rate of rise of leakage, which is the rate at which your system develops new, hidden, unreported leaks. It'll be important to match the frequency of surveying to the volume of water that you recover through that survey, such that you're not spending too much money to pursue unreported leakage, or alternatively, spending too little money and incurring an excessive volume of unreported leakage losses. This is a typical example of a rate of rise of leakage in a utility that does not pursue proactive leak detection. This was a system that chose to monitor their losses with a water audit and component analysis on an annual basis, but didn't interact or intervene against their leakage. And so the system just continued to accumulate leakage at its rate of rise. So once this system starts proactive leak detection, they'll initially recover a lot of this volume of leakage. Much of it is cost-effectively recoverable for them. And then they will combat that trend of increasing leakage through time with periodic and scheduled surveying. Of course, when you're thinking about leakage, a lot of leakage results from overpressurization of the system. And so when you want to attend to all forms of leakage, whether background leakage, unreported leakage, or reported leakage, pressure management and engagement with your system's pressure dynamics will serve you well. Pressure management and optimizing the pressure dynamics of your system will reduce the frequency of your breaks, as well as reduce the volume lost to each instance of failure. You'll want to think about how you know the pressures in your system before you intervene and change your pressure dynamics to the extent reasonable and effective. The important part of pressure management is to identify areas that are overpressurized, which is best accomplished with some field surveys and with some hydraulic modeling, such that you can appreciate where there is opportunity to reduce pressure and therefore reduce break frequency, leakage losses, and extend infrastructure life. Pressure management and engagement with system pressures also offers other benefits. For example, by studying your system pressures, you may identify pressure transients or water hammers that you didn't know about that are nonetheless damaging your infrastructure with each occurrence. Those sorts of findings are often unexpected benefits of engagement with system pressures. As I mentioned, pressure management, of course, reduces the frequency with which your infrastructure fails. And there are some studies out there that suggest both the break frequencies that are typical and that are optimized. And if this is of interest to you, I encourage you to delve into the component analysis Water Research Foundation 4372 model that does aggregate studies of break frequencies to describe typical and optimized performance. Lastly, in the realm of reported leakage, leakage that you've already come into contact with and contained, in future years, if you'd like to reduce that volume, your best tool will be improving your response times, such that the leaks that you do attend to, that come to you and make themselves known, are repaired faster, and the losses to each instance of reported leakage are less. Usually, folks will accomplish this by increasing their capacity for repairs and by hiring additional field crews to attend to leak repairs. But it's also possible that some adjustments to procedures and protocols that govern leak repair, like prioritization of leak repairs, as well as the data management and allocation systems for leak tracking, those can be streamlined such that you attend to leaks faster and more efficiently. But simply put, faster, better repairs reduce leakage volume, and should your reported leakage compose a large portion of your total leakage, increasing your capacity for repairs can be beneficial. Once you've thought about the types of leakage in your system and valued the interventions against those volumes of loss, you have the chance to design a water loss control program that can be refined with years of use and help you to achieve a cost-effective level of water loss. We started in this whole workshop with determining volumes of loss through the AWWA water audit. The water audit gave us a breakdown of the total apparent loss volume and the total real loss volume, but didn't go much beyond that. To get a deeper insight into the leakage profile of a system, you have to do a component analysis. It's also helpful to think about the sources of apparent loss and the particular metering populations that are contributing to under-registration and revenue loss. And all of those component analysis activities are deeper analyses and engagement with data that provide the information that you need to do a water loss control program. Once you understand the types of losses occurring in your system, you can then evaluate the economics of water loss recovery. You'll want to think about how you value your water losses. Typically, apparent losses are valued at retail rate, since more accurate customer meters would likely produce more revenue for you at retail rate. Conversely, real losses are valued in a variety of ways. Most utilities start by valuing real losses at production cost, simply to acknowledge that by containing leakage, they do not have to supply as much water into the system. It's also possible, though, for real losses to be valued to incorporate things like avoided liability from repair of catastrophic failures, or to also consider things like marginal supply development. If you contain your real leakage losses, does it mean that you can defer constructing a well? Perhaps, and perhaps that should be incorporated in your valuation of real loss. Once you've decided how much your water losses are worth to you, you should then balance the value of that loss with interventions against water loss. So you'll need to think about what it costs to survey your system for leaks. You'll want to think about what sort of time and materials costs you would need to cover in order to increase your repair capacity. You might want to evaluate what it would look like to change out malfunctioning meters in your customer meter stock. By balancing the costs of your losses and the cost of intervention to achieve a minimum cost point, you can design your program. And then lastly, once you've appreciated the magnitude of intervention that's appropriate for your system, you'll want to implement those interventions. And you'll want to do this over the course of a couple of years and collect the data through time that helps you to assess whether what you're doing is actually resulting in reduced volumes of water loss. The goal with any water loss control program is to start with a manageable level of work and engagement with the system, and to refine it through time such that you're continually monitoring your system, and rather than being reactive to its shortcomings, you are instead proactively engaging with them to minimize the total cost of intervention and water loss. In all of this process, of course, the efficacy of water loss control and your ability to target your interventions does depend on the quality of your data sources. So we spent a lot of our early discussions of water loss in the realm of water auditing and component analysis discussing uncertainty and the value of having reliable data in informing a water loss control program. If upon completing some of those preliminary analyses, you don't have data that's good enough to serve as a picture of system performance, you'll first want to get better data before you intervene against water loss. All of this does lay on a bed of data, and it's worth getting your numbers right as you engage with your water losses.
With that, we'll pop over to case studies. Before I do that, does anybody have any last burning questions about water loss control program design? We tend to encourage folks to think in terms of multi-year scales versus months or decades. A lot of folks will design their first programs to happen over 3 or 4 years as a starting point. All right then. So the case studies. The Alliance for Water Efficiency received a grant from the Charles Stewart Mott Foundation, which is located in Michigan, to look at how what community-scale water challenges can be addressed through water loss control. And on the surface, that speaks to system management and distribution efficiency, but it also has implications, for example, for ratepayers and for the public. When a system is efficiently run and isn't incurring excessive water losses, the ratepayers receive the benefit of efficient rates. And so there's certainly the utility-specific focus of maintaining infrastructure of integrity, and that is efficient, but the public benefits from that exercise as well. So that was one thing we were thinking about. And also, how do we have this regional conversation about what our water's worth and what we're doing to steward it? The Great Lakes are a national treasure. I know, having actually jumped into all 5 of them, that there's something to be protected. So that's why we're in this room for this workshop. There'll also be this webcast available online after we do this. Publication materials will come out related to this project, and we hope that you'll just keep your ears open for subjects of water efficiency and water loss control. So in our case studies, we worked with Madison Water Utility, located here in lovely Madison, Wisconsin, and also the city of Ann Arbor in Ann Arbor, Michigan. On the surface, you might think that those were similar places, but that each system had some unique characteristics. Madison, a little bit larger in terms of service connections than Ann Arbor, and more miles of main. And when we think about miles of main in a water audit perspective, we're talking about all pipe 4 inches and larger, so that includes standard distribution and transmission main, but also things like hydrant laterals and very large diameter service connections. So we included that. Madison is about double the mileage of pipe as Ann Arbor. Madison also runs off a bunch of wells, whereas Ann Arbor has a single treatment plant that feeds into the distribution system. So another distinguishing factor. Madison Water Utility embarked on an AMI project that overlapped with our selection of a 2014 audit period and made for some fun with data. I have a colleague who, when he realized that he'd be working with a combination of manual read and AMI data and this very intriguing data set, his eyes lit up. The programmer in him thought that was fantastic. So that was something to reckon with. Madison also has a series of pressure zones that aren't perfectly hydraulically discrete, but are management zones. Ann Arbor has half that number. And in Madison, we worked with calendar year 2014. In Ann Arbor, we worked with fiscal year 14-15. Does anybody remember January of 2014?
Yes.
I'm seeing traumatized faces in the room. It was really cold. I was living in Minneapolis at the time and remember one morning putting on 4 pairs of pants to walk out the door. So that's something also to reckon with. We think that we will see increased volumes of loss in this particular audit period because break frequency went through the roof, and the question is, does that manifest in our audit results? So that's something to keep an eye out as we talk about our water losses. So our 2 case studies, Madison and Ann Arbor. Thank you, by the way, for participating. Very appreciated. So to jump right to the chase, we walked through the process of a water audit and a component analysis for each of them with their individual data sources and got different results. As we think about data, I'd like to first discuss some of the things that were wrenches in our analyses. With Madison, it was this billing transition in the middle of the audit period where their AMI system went fully online. It had been installed up until that point and then happened in the programming sense during our audit period. And so there was a migrating of billing data systems and a change from a less than monthly billing frequency to a monthly billing frequency. And so we had to figure out how to make sure that in the process of transition we weren't duplicating volumes or dropping accounts or finding ourselves with mysterious gaps and zeros. And so we did actually, in working with very raw billing data, like a single record per bill, so on the order of perhaps 1 million rows in our final file, that compound meters had been duplicated or appeared to be duplicated in our raw billing data export, wherein because each meter had 2 registers, we received 2 entries, but the billing software program summed the volume across each register and then duplicated that. That was something that we had to figure out what we're going to do about. And it's worth noting that if you do work with raw billing data, things that you may see in the raw data may not actually have manifested in the bills that you sent to customers. The billing software often has internal cleanup processes, and your billing folks in that process probably deal with that as well, but then when you go to that initial base data table and pull stuff out of that, there could be some funkiness going on in there. So it's an interesting chance to interact with the billing process and the software settings. That was something we had to work with Madison. With Ann Arbor, we had an interesting situation at their treatment plant where we pulled SCADA data to describe their 4 effluent meters and realized that the volume we were looking at was just massive, and it didn't at all compare well to what they were selling. And we, in talking with their treatment plant operators, learned that they have a scenario in which, depending on how they're balancing demand across their zone, they have a valve that they open and close at their treatment plant that either will put meters in parallel or in series and may duplicate volumes in the process. And the question is, well, when was that valve open and when was that valve closed? And we had no record of that. So we didn't know when the meters were registering independent volumes and when they were registering redundant volumes. And so we had to work with records of pumping wattage to figure out which pumps were on related to the valve position. And it was a rough proxy, but it sort of got the job done. But still, with that sort of information, the results of our audit are uncertain. And so now moving forward, Ann Arbor has, an Excel spreadsheet where they note the position of the valve on a daily basis and indicate when they open it and when they close it. So it's a very simple fix to a problem that affects the fundamental volume of our water audit. So those sorts of things come up, and everybody's got their own unique scenario. We also had SCADA data go offline for 6 days in Ann Arbor due to a power outage and a system update. And so we had to fill in a lot of holes there with some assumptions. And then last thing, something interesting that we noted in Ann Arbor, but I think probably was the case in Madison as well, 1% of their meters, customer meters, were responsible for measuring 40% of the sales volume. I think it's the University of Michigan we're talking about. And so the question then in their apparent loss work and in their revenue generation studies is, what do you do about those really big hitter cash cow meters. How do you make sure that those are generating the revenue you need them to, given that 40% of your revenue is coming from 1% of your meters? There's a lot you can do there. So that was just something interesting to reflect on. And we came across that in working with their billing data. And they knew that that was a thing, but didn't have the numbers to talk about it. So that was a fun task. In the results world, Madison had higher water losses. Again, here we are. We're not talking about percentages. We're talking about gallons per connection per day. And, of course, higher water losses translated to higher value of water. The infrastructure leakage indices, Madison came in around 4, and the City of Ann Arbor at around 2. Again, with the margins of error on these numbers, I'm rounding them to 4 and to 2 because I don't think we can say with certainty to the nth degree what their infrastructure leakage indices are. And then comparable data validity scores that indicate that the data is good enough to start being insightful, but there remains a lot of room for improvement in data accuracy and data quality. Commonalities across the two were that we didn't have the information available and in a form that could be analyzed to talk about instrument accuracy, both in terms of production meters. We didn't have test or calibration certificates, particularly the volumetric testing, to talk about meter accuracy, either because they hadn't been tested or they just were in a configuration that couldn't be tested. So right off the bat, we're not sure if there is any error around our production volume there. We also didn't have any test data in a tabulated digital format to be able to talk about customer meter accuracy. It's one thing to test customer meters and to confirm that they're working and throw them on a test bench. It's quite another to record and analyze those tests. And I think moving forward, it will be helpful for folks to get that information into a spreadsheet such that we can appreciate how that overlaps with the consumption the meters actually do see to appreciate apparent loss. We did the water audit, we got our volume of real loss, and then we moved into the world of component analysis to disaggregate that real loss even further. The results came out similarly in that background leakage is a large chunk of the pie for both utilities. We're seeing a lot of those seeps and drips, probably accumulated with older infrastructure and harsh winters. That happens. The reported leakage, the leakage with which the utilities interact, is a smaller slice of the pie. Of course, our ability to calculate that depends on the repair records, and those were effective for the purposes of determining the total count of failures, but in each case had either missing or incomplete information. For example, in Ann Arbor, we worked with repairs that sometimes had complete timestamps and sometimes not, which is understandable because repair people in the field are focused on the repair more than the data collection, as they ought to be. But moving forward, it will be helpful to work on institutionalizing that process of data collection to inform something like a component analysis. And then lastly, the volume of hidden losses as a total portion of the pie is slightly larger in Madison, slightly smaller in the City of Ann Arbor. We're looking at the dark blue now. That's the ongoing leakage that is acoustically detectable, so it's unreported, but hasn't yet been found. So the question is, how does the value of that leakage compared to what it would cost me to go after it with proactive leak detection? And in considering that question, we're not worried about the cost of leak repair because the leaks already exist and it is assumed that you would repair them at some point. It's just a question of when. Some uncertainty does persist in our component analysis with both. I wouldn't bet my firstborn child on this, but it's insightful as to where to go next to attend to leakage in a pilot manner, and then to refine your data collection systems to get this more narrowly honed in the future.
And do another audit as well, right?
Oh yeah. Goes without saying, auditing is an annual practice, right? So recommendations moving forward. With Madison Water Utility, there was enough ongoing hidden leakage in the system that it would be cost effective to clear the backlog of leakage. The value of the leakage is in excess of the cost of intervening against it. And so the recommendation is start doing leak detection and focus initially on the zones where you suspect leakage is worse and go from there, refining your leak detection as you learn about the leakage in your system. With Ann Arbor, the value of leakage was less than the cost to intervene against it. And so our recommendation there is to continue to do this exercise of compiling a water audit and doing a component analysis to track it such that when those hidden losses accrue to a point where it's break even or cost effective to do leak detection, they should do that. So when you do a water audit, it may suggest that you should jump into the field and start acting, or it may suggest that your best approach is monitoring. But that sort of thing you can't know until you do this investigation. For both, we recommend considering zonal management of leakage. When you think about deploying leak detection, it feels like a little bit of a shotgun approach to say just do the entire system periodically. It's effective, but it's also expensive, and it may behoove you to focus on smaller zones, especially those where leakage is greatest. And you can do that by either in a discrete or in an open manner, monitoring all inputs into a zone, appreciating customer consumption, and having sort of small zonal water balances and doing a water audit for part of your system so that you can figure out where the leakage is most severe.
Does that concept make sense? Have you heard about it? It's really an attempt to get away from this random nature of starting leak detection on one end and ending it at the other end and then starting over again, right? To dedicating your resources towards those areas where actually leakage is happening. Because you all know your system is not uniform in terms of its performance, right? And once you have the data that you're monitoring, this is how much goes into a zone, this is the consumption in my zone, the delta leakage is X. You can also then say, well, for that zone, it takes me so much to survey it, so even I know I have some leakage going on in there, it's not cost effective for me yet to go in there. I'm only going to send someone in there once it exceeds a certain volume. That's really the most advanced and refined way of deploying resources and managing leakage.
Mm-hmm. And especially in a system that has AMI data, for example, that sort of zonal management can be really effective because you can get information about leakage development almost instantaneously, depending on how willing you are to dig into AMI programming. It can be a wonderful management tool and a very good use of your AMI data. For both systems, we recommend collecting information about meter accuracy. On the production meter side of things, that means designing a robust volumetric or comparative test protocol and then going and doing that. You can either work with a reference volume where you either draw down or fill up a tank of known dimensions to figure out a reference and then compare it to what the meter picks up. Or you can work with an insertion meter or a strap-on meter or some meter of known accuracy to look at the meter whose accuracy you don't know. On the customer meter side, I believe Madison does test customer meters, but for our particular audit period, those hadn't yet been tabulated, and so they were in a bunch of pieces of paper, and it was data that, given our time of the project, couldn't inform the audit. But moving forward, that happens. When we think about customer meter testing to appreciate apparent losses and talk about meter management, we speak in terms of two distinct groups, small meters and large meters, with a threshold at 3 inches. 3 inches and larger is a large meter, 2 inches and smaller is a small meter. Generally, there are so many small meters in the system that testing all of them doesn't make any sense. And instead, the question is how to statistically sample those meters such that you get a random and representative sample. On the large meter side of things, go for the cash cows. Go test the meters that supply the University of Wisconsin and figure out how those are doing, whether they're generating revenue efficiently or not. And then, of course, do this all the time. Water audits are most useful as a tracking tool, wherein they get better every year and you can start to appreciate how your system performs through time. And I promise that once you do this once or twice, it gets easier and the data pathways that you use get a little bit more greased and people get accustomed to thinking about the system in this way. And then takeaways more broadly. You've heard us say this all day, but I think that these two case studies prove this. Data doesn't have to be perfect in order for it to be useful. You can learn from imperfect data. You can learn from the gaps in your system's measurements. The water audit can accommodate your system. I promise you that it can. You will just have to work with your colleagues to figure out the best way to do that. And I'm sure that you have a lot of internal resources, both in terms of the history of your system and the expertise of your peers to figure out how to use the water audit once you have a broad appreciation for how the pieces fit together. Secondly, as is the distinguishing factor between Madison and Ann Arbor, the water audit and the component analysis and the economic modeling may suggest that immediate water loss intervention is to your benefit, or it may suggest that it's better to take a monitoring approach and watch and be ready to react when cost-effective opportunities arise. But you can't know that until you dig into your data and until you measure your system's efficiency and think about how much your water's worth. So information in this instance is your friend. You need a component analysis of water loss to plan water loss control. Had we just taken the total volumes of leakage for both systems from the audits and attached a dollar figure to them and said, go after it, we wouldn't have known where to go. And so it's important to work on leakage profiling once you've got your audit in a place that feels good. And then lastly, there's no one-size-fits-all approach. We encourage both utility folks and their regulatory peers to remember that there is no prescriptive plan that works for everyone. All systems have unique costs, unique physics, unique inherited data and structural challenges that make water auditing a very individual process. So those are the broad takeaways from our work with both Madison and Ann Arbor. I encourage you to speak with Tom as the Madison representative, and can certainly put you in touch with the folks at Ann Arbor if you're curious what their experience of this was. But when done effectively, again, water loss control makes your system a more viable system financially and in terms of sustainability of supply. And the public benefits from that as well. So I encourage you to think about this both in terms of business efficiency, but also in terms of public responsibility. As America at large is dealing with aging infrastructure, reaching a point of needing significant reinvestment, it's a great opportunity to build systems that can be managed with a lens of water loss control. This is certainly an analytical exercise, but it's also a management tool and a holistic perspective, thinking about how we steward our water resources such that we are maintaining our ability to do our job and protecting public interests at the same time. And if you need to go to sleep or have a pillow, we have AWWA M36, 4th edition. One of the authors is in the room. There were many other experts that contributed, and through its 4 editions has gotten even more in-depth. The Water Research Foundation has a bunch of available reports online, ranging from leakage management technologies to studies of metering accuracy. There's a particularly interesting one where a laboratory in Utah purchased meters through utilities from meter manufacturers and tested them new to see how they did. The results were surprising. There's also the component analysis report, and I'll put a plug out right now that we are writing the report on water audit data validation that's due out this fall or winter. We'll see. But that's happening. And then there are textbooks. Reinhard also wrote this textbook. It's scintillating. And then there's the audit software.
Buy it on our website.
There you go. This is Water Loss Control, the 2nd edition. And then there's the software tool that's available from AWWA for free. It's the best practice tool and moves you away from unaccounted for water into the exciting journey that is water loss control.
All right.
Any questions before we move on to the next section?
Which is no longer us. So, all right then. Thank you very much for your attention. I hope we can open it up to some other people.